Greetings and welcome to the series of lectures on systems of equations, 4.7, Matrix Solutions to Linear Systems. We're going to start using matrices to solve linear systems of equations. And I guess the starting point is, what is a matrix? A matrix is just a rectangular array of elements that's considered as a whole. So it's a whole bunch of values, but it's considered as the whole thing. Can't just look at one little piece. We're looking at the whole entire thing. For a linear equation in two variables, let's just say x and y, here's what we can do. From this system of 2x plus 5y equals -4 and x minus 3y equals 9, we can represent that system by a matrix. Here's what we do. We put it in brackets, first and foremost, and then we just pull out the values, the coefficients, and the constants. So 2, 1, 5, -3, -4, and 9 are the values we're going to pull out. 2, 1, 5, -3. We put a line in between just to kind of let us know that that's where the equal sits. -4 and 9. This is what's called an augmented matrix. It means it includes the coefficients of the variables as well as the constants. So what can we do with a matrix? So what? We have this matrix. Now what do we do, right? Well, there are operations that we can do on a matrix. In fact, there are 3 that we're going to discuss. The first one is we can interchange any 2 rows. That means we can swap them. So if this is row 1 and this is row 2, I can swap them and write row 1 as row 2 and row 2 as row 1. That's the first thing we can do. We can swap, interchange. The second is we can scale a row by multiplying it by a non-value constant. It means I can take the first row, multiply it by 2, right? We can do that. And it doesn't, as long as I multiply each element of that row by the same amount, it's called scaling, then it doesn't affect the ultimate solution set. The third is I can add any row by a constant multiply of another row. For example, I can take row 1, or better yet, I can take row 2, multiply it by -2 and add it to row 1 and leave it in row 1. That's something I can do. So I can scale a row, add it together, and leave it in that new location. That is this third operation. Okay, so we have these row operations, but how does it help us? Well, if we can get an augmented matrix to look like 1, 0, whatever value, 1, whatever value, whatever value, then I can solve this system fairly simply by back substitution. Okay? And I say that lightly because sometimes the numbers aren't quite nice, but if I can get it to equal 1, 0, something, 1, something, something, I don't care what these somethings are, then I can back substitute back into the equations and solve the system. Because here's what this augmented matrix means. When we have finally transformed our matrix to 1, 0, something, 1, something, something, I can translate this back into linear equations. That's going to be 1x plus something equals something, and no x's but 1y equals something. Well, y equals something. Then I plug it back into the first equation and I can solve for x. So this back substitution helps. That's what this transformation gives me. It gives me a value for y so I can plug it back in to get the value of x. Alright, let's use row operations and let's solve the system using row operations. Alright. First thing is I have the linear equations of 2x plus 5y equals -4 and x minus 3y equals 9. I need to get that into the augmented matrix. Okay, so that's going to be bracket 2, 1, 5, negative 3, negative 4, 9. So it's going to look like this matrix. Then I have to decide, my ultimate goal is to get a 1 in this first position, a 0 in this next position. Don't care what's up here in the 5 position. Well, 5's sitting there right now. But in this negative 3, I want it to say a 1. Okay? Looking at this augmented matrix, if I interchange row 2 and row 1, a 1 will be sitting exactly where I want it. So let's interchange row 1 and row 2. Okay? So 2, 1, 5, negative 3, negative 4, 9 becomes 1, 2, negative 3, 5, 9, negative 4. All I did was swap those two rows. My goal next is to get this 2 to be a 0. If I multiply row 1 by negative 2 and add it to row 2 and leave it in row 2, that will give me a 0 there, because negative 2 times 1 plus 2 is 0. That's what I want. I want that spot to be a 0. So let's do that. Let's multiply negative 2 to row 1, add it to row 2, and leave it in row 2. All right. Negative 2 times 1, negative 2 times negative 3, and negative 2 times 9 will give us negative 2, 6, negative 18. Let's add it to row 2. Negative 2 plus 2 is 0. 6 plus 5 is 11. Negative 18 minus 4 is negative 22. Let's put it in to row 2. I'm getting there. Almost there. Right? I have a 1, I have a 0. I need this 11 to look like a 1. I think if I multiply it by 1/11th, well, 1/11th times 11th will give me 1. But what I do to one value, I have to do to all of them. So let's multiply 1/11th by row 2 and put it back into row 2. Well, 0 times 1/11th is 0, so that doesn't change. 1/11th times 11 is 1. And 1/11th times negative 22 is 2. Therefore, my new augmented, and I'm putting it back into row 2, is 1, negative 3, 9, 0, 1, negative 2. And I know I've said it vertically before, but I'll just go ahead and say it horizontally. All right, I have the matrix I need. 1, 0, and 1 are all in the places that I need. So how do I use that? I rewrite the matrix back into equations. 1x minus 3y equals 9, and y equals negative 2. Now that I know that y is negative 2, I can plug it back into the first equation and solve. X minus 3 times negative 2 equals 9. X plus 6 equals 9, therefore x equals x equals 3. So my solution set is 3, negative 2. I think the hardest part about using this matrix augmentation and transformation is just trying to kind of come up with a plan of attack. How do I want to conquer this problem? Once I figure out which rows I want to manipulate, then I can use my row operations to do that. All right, let's start from the beginning and solve a system of equations not with 2 variables, but with 3. Maybe I'll have to do more steps to come up with my matrix that I want. In essence, I want a 1, 1, 1, and everything below the 1s I want 0. That's my transformation matrix that I want. Right? So here's my system of equations. X plus y minus z equals 2. 2x plus 3y minus z equals 7. And 3x minus 2y plus z equals 9. First thing is to translate my linear system of equations over to an augmented matrix. 1, 1, negative 1, 2. 2, 3, negative 1, 7. And 3, negative 2, 1, 9. There's my augmented matrix. Since my goal is to get a 1 in the first position, I'm not going to change row 1 at all. I'm going to leave it there. My second goal is to get a 0 under the 1 in the first position. So here's what I think I'm going to do. I'm going to multiply row 1, I'll call it R1, by negative 2. That will give me a negative 2 in the first position. And if I add it to row 2 and leave it in row 2, it will become a 0 in that first position. All right. Negative 2 times 1 is negative 2. Negative 2 times 1 is negative 2. Negative 2 times negative 1 is 2. Negative 2 times 2 is negative 4. I'm going to add that to row 2. 2, 3, negative 1, 7. Negative 2 plus 2 is 0. Negative 2 plus 3 is 1. 2 minus 1 is 1. And negative 4 plus 7 is 3. So my new row 2 is going to be, I didn't touch row 1 or row 3. 1, 1, negative 1, 2 for row 1. And 3 I didn't touch. 3, negative 2, 1, and 9. But the new row 2 is 0, 1, 1, 3. All right, exactly what I want. I want a 0 right underneath the 1. But I want a 0 where this 3 is in the third row. So I think if I multiply row 1 by negative 3, add it to row 3, and put it back in row 3, I will have a 0 there, because negative 3 plus 3 is a 0. Okay. Multiply. Negative 3 times 1 is negative 3. Negative 3 times negative 1 is, negative 3 times 1 is negative 3. Negative times negative 1 is positive 3. Negative 3 times 2 is negative 6. I'm going to add it to row 3. 1, 9. There we go. All right. Negative 3 plus 3 is 0. Negative 3 minus 2 is negative 5. 3 plus 1 is 4. And negative 6 plus 9 is 3. So that goes back into row 3. I did not touch row 1 this time. And I did not touch row 2 this time. But I am going to change row 3 by my row operations that I did. 0, negative 5, 4, and 3. All right, we're getting there. I have a 1, 0, 0. Now, my matrix that I want, next to the 0 I want a 1. Hey, I already got a 1. But underneath this 1 I need a 0. So I'm going to use row 2. I'm going to multiply row 2 by 5, add it to row 3, and put it back into row 3. That should be an arrow, really, and not an equal. If I put it back into row 3, that's going to be 5 times 1 is 5, minus 5 is a 0. That's exactly what I want here, is a 0. All right. 0 times 5 is 0. 5 times 1 is 5. 5 times 1 is 5. And 5 times 3 is 15. Add it to row 3. 0, negative 5, 4, and 3 gives me 0, 0, 9, and 18. So let's rewrite our matrix. 1, 1, negative 1, 2. 0, 1, 1, 3. And our new row 3 is 0, 0, 9, 18. Awesome. We are almost done. Almost done. All right. I need that 9 to look like a 1. Well, if I multiply it by 1/9, everybody in this row by 1/9, I'll get that to look like a 1. So let's multiply 1/9 to row 3 and put it back into row 3. right? 1/9 times 0 is still 0. 1/9 times 0 is 0. 1/9 times 9 is 1. 1/9 times 18 is 2. Here's my new matrix. 1. Didn't touch row 1. Didn't touch row 2. I did change row 3. 0, 0, 1, 2. Yay! We're done with all the heavy calculations. Yay, we got our matrix to look exactly how we want it. Here's what this means. This means x plus y minus z equals 2. That's the first row. Second row, y plus z equals 3. Third row, z equals 2. Well, if z equals 2, then y plus 2 equals 3, meaning y equals 1, right? Because 1 plus 2 is 3. And if z is 2 and y is 1, then x plus 1 minus 2 equals 2. Well, x plus 1 but minus 2, that's x minus 1. Therefore, x must equal 3. 3 plus 1 is 4, minus 2 is 2. 2 equals 2. So here's our solution. 3, 1, 2. Kind of cool, huh? Kind of a lot of work. Thinking ahead, trying to figure out what the goal is and how to best get there. There's lots of ways to get to this matrix. But trying to figure out to solve the puzzle, it's like a big old puzzle, I think is kind of the cool part about this method of solving system of linear equations. So that's it for this video. Until next time, be seeing you.